So today we're going to seriously solve the first problem of the practice exam for the second exam for Engineering 110, which covers continuous Fourier transform, signal analysis, discrete Fourier transform, signal aliasing, spectral leakage, all that good stuff. So let's go ahead and just dive right in. So just kind of be clear. So you're going to have 90 minutes to do the exam, 30 minutes to submit. Everything's open, so use Mathematica, use MATLAB, whatever you're comfortable with. Make sure you get those submissions in on time. The exam 2 will cover materials in lectures 8 and 9 and on P-sets 5 and 6. So if you study those and this practice exam, you should be good to go. So let's take a look at the first problem in this exam. So question 1, don't be a square, use CFT. I like to use puns in my example problems. It says, consider the following analog signal. We see a plot of voltage versus time here. Voltage in volts, time in seconds. Be sure to make sure to, what is your time unit, because that is critical for your Fourier analysis. For this problem, we only consider the first 5 harmonics, so we know that we're going to plot from n equals 0 to n equals 5. And after that, that's it. So it's asking what is the dominant frequency, what is the maximum frequency, what is the fundamental frequency. So let's go ahead and try to solve this. So first thing, whenever you're dealing with basically a signal, we see here we're not given these discrete series of points. Instead, we can kind of describe mathematically what is this function at every kind of point along here. So we know, basically what is algebraically, what is our y of t. So we don't have to use DFT. We are instead going to use CFT for this problem, in case the problem statement didn't kind of hint to that. So the other thing we want to kind of think about is, what about our signal? Is our signal periodic or is it aperiodic? Well, looking at this signal, it goes flat, rises to 5, goes to 10, drops down, -10 again, rises to 5. So after 3 seconds, we are periodic. So our shortest period is t equals 3. So that is our period. If we know that, we know that our delta f, our fundamental frequency, our lowest frequency, which is going to be 1 over t. Not that. So that is our delta f. We also know that we are only interested in the first basically 5 harmonics. So we know that our f max, our maximum frequency, is going to be equal to maximum number of harmonics times delta f. That's it. So we've already answered B and C without even doing any kind of Fourier analysis. But in order to find the dominant frequency, we need to plot our Fourier spectrum. So we need to calculate our number of harmonics. So to do that, we first should look at how can we describe essentially this function between our period 0 and 3 seconds. So we know that, let's start to write out how we could kind of break this down piecewise. So our first function from 0 to 1 is just -10. Our second function from 1 to 2 is just 5. Our third function, well, that's a linear line, and my phone just went off. Apologies for that. Let's find what that function is. So we have Mathematica, so I'm going to fit. My points are going to be at 2, it is 5. So at 2 seconds, my voltage value is 5. At 3 seconds, my voltage value is 10. I want to fit this linearly because it looks like it is definitely linear in that range. So that's my expression. So I'm going to put it in terms of t minus 5. And I have my y list, which is the list of my piecewise functions. We'll see why I'm doing this as a list form in a second. And I have my interval values, so when these functions are valid. So the first one's from 0 to 1, the next one's from 1 to 2, pretty straightforward, and then 2 to 3 in this problem. So to calculate my harmonic coefficients, I know that I have to do my a sub n. That is going to be 2 over t times integrate my y list, the first value, and I'm going to multiply it by cosine of 2 times pi times n times t divided by my period t. And I'm going to integrate that from t goes from interval. Let's look at this interval values here. Interval, if I look at table form, I want to integrate this first function y sub 1 from 0 to 1. So this first function, y list, I'm grabbing the first one, this here. I want to grab it or integrate this from interval. I want to grab the first row and the first column to start off with. And then I'm going to grab the second row, or first row, sorry again, first row, second column. So I'm going to integrate from 0 to 1 for this first y sub 1. That's it. So I need to repeat this function. So I need to do a table. I'm going to iterate from here here, here, from I from 1 to 3, or the length of my Y list. And I need to take the total because I need to basically add all those values. That's it. Mathematics thinking, thinking, thinking. That's all it is. That's A sub n. What about B sub n? Well, my B sub n is going to be simply this, but now it's going to start thinking. Excuse me. Sorry about that. Oh, let me go back here. Excuse me. We'll get that going again. Sorry about that. So B sub n is going to be the exact same thing, except we're going to have a sign value here, and we just shift enter. That's it. So that's A sub n. We've got B sub n. What is B sub 0? Well, that's just going to be 0, right? Because if I plug in for n equals 0, sine of 0 is 0. What about A sub 0? If I plug in for 0 here, cosine of 0 is 0. I know you guys know this. I know you in stats, you go over your the basics of your trig functions, so you're all experts on that. So all you do is plug that out, plug it in for 0. That's A sub 0. So now I can kind of start to plot my frequency spectrum. So I'm going to transpose basically this list of table, and I want to go to I times delta f from I from 1 to 5, and I want to transpose that with another table of the square root of A sub n squared plus B sub n squared from, and I'm going to select replace n goes to I, where I goes from 1 to 5. That's it. So I'm going to close that. Parentheses. I can show this value numerically. There it is. I also want to kind of put in that first your A sub 0, your 0 order harmonics into your expression. So I'm going to do that by putting in 0 and A sub 0, excuse me, at the first unit. That's it. So now I can get fancy with my list plot. So list plot, I'm going to grab this guy, all of it here, paste it in here, and then I'm going to do plot range all, I'm going to do frame true, I'm going to do image size 1000, I am going to do frame style directive, all the rest of this is just getting, just plotting nicely in Mathematica, so not too critical for your exam. You're not going to be graded on how nice your plot looks. That's for your lab reports. Not really kidding on that one. So make sure you make your plots nice and neat. And plot style. And the good thing about this is once you do this once, you could just kind of copy and paste. And we'll see. I'm going to do that in the next video, so I'm not going to kind of retype this out. So go ahead and make sure to do that here. And then I'm going to do filling. Let me close this. Filling bottom. And I'm going to make this nice plot right here. Oof, that's a little bit 005. So let me zoom out. Zoom out even a little bit more. So now we can see our frequency spectrum. So our harmonic coefficients plotted here, our frequency here in terms of multiples of delta f, and I can see my dominant frequency is actually my fundamental frequency. So the one with the largest amplitude here, that is my dominant frequency, and that happens to be my fundamental frequency in this problem as well. So that's it. We've done A, B, and C. And then for D, this is a pretty nice little question here. So let's maximize this if at all possible. Here we go. And let me, let's go. Here we go. So it says, I plotted the Fourier series above. Why is my fit not approximating the original signal? Well, how do we improve our fit in Fourier series? Well, we increase the number of harmonics. So clearly in this signal, if our Fourier series, our blue curve, is not approximating our original signal, our red curve, we haven't plotted or we haven't included enough harmonic, coefficients. So remember, the beauty of Fourier series is that, or Fourier analysis, is that you can approximate any signal with an infinite series of sines and cosines. So again, as you increase the number of harmonics, your fit should be better. If you decrease the number of harmonics, or you don't have enough harmonics in your kind of Fourier series, then your fit is going to be poor and poor and poor. So that's it. Just a qualitative answer on this one, just to double check. Again, I want the physical meaning of this Fourier analysis. So that's it. Problem 1 done. Now let's move on to problem 2. See you in the next video. Bye.